I am the ICU-DDR Coordinator for Educational Programs and Regional Support. No worries if you have missed the previous lectures, you can view them on ICU-DDR's YouTube channel, and we'll also send you a copy of the previous slides. Please check an email from either me, Caleb, or Carly regarding the recordings and workshop materials. Some guidelines for today's event: please make sure that your microphone is turned off. And if you have questions at any point during the presentation, please use the chat box and we will relay them to the speaker. And he's also checking the chat box for any of your questions. As a reminder, this workshop is being recorded and we will send you a copy of Dr. Cosgola's PowerPoint presentation as well. During the course of the workshop, we will have a 15-minute health break in between the 3 hours. And lastly, translation for closed captions for various languages are available. To turn on this feature, you can click the CC Captions icon at the bottom of your screen. And if it's not showing up, click the 3 horizontal dots that says More, and then you can select the closed caption language of your choice. It seems that there will be a few of you joining us for the first time today. So let me reintroduce our facilitator. So our facilitator for today has a PhD in engineering and is all but dissertation in his second doctorate in social work. He is a researcher who specializes in adolescent substance use and a holistic system thinking approach to network analysis with the application of various engineering tools. His goal is to understand the factors influencing youth behavior and develop effective interventions that support community well-being. ICU-DDR is very pleased to have with us an expert who is generously sharing his expertise and time to teach all of us. Ladies and gentlemen, let me turn over the floor to our facilitator, Dr. Janaka Kosgola. Sir?
Yes, thank you. Thank you so much. So I appreciate that. So I just shared my PowerPoint presentation. So hold on. I just have to hit enter. Then you will have it. So it should be in the chat. You should be able to download. So it's the PowerPoint. So you can copy and paste the code snippet that I have. The scripts are scripts that we have here. As we go. So last week we learned a lot of basics regarding R and its functionalities. This week I am focusing on, so we are going to study a little bit about modeling, so how to really perform tests and then work with data to understand what hidden behaviors are between the variables and how they are interrelated. So today I'm assuming you have some background on basic statistics, such as hypothesis testing, what null hypothesis is and alternative hypothesis is. And I'm assuming you know these things and what the F value, P value, T value, all these things. So I have some definitions here, but I'm not going to go over all of that because we are here to learn not the fundamentals of statistics. So we'll start with the hypothesis testing because that's what we mainly do, as the first step in this analysis, and then we'll go into some advanced modeling, and then we also will have a full analysis session tomorrow. So tomorrow's session, I'm not going to have a regular PowerPoint presentation, but instead we have a data set and we'll work on the analysis. But today I have a full PowerPoint session. We'll see how far we can can get to, like through the slides. If we can finish everything, then we can dedicate the entire day tomorrow for the analysis, or else if there's something left, we can finish that and then do the analysis tomorrow. And then day after tomorrow, I also have planned some other, like, kinds of modeling. So basically predictions based on the developed models. We'll look into that. That's like my plan for the week. And let's start with hypothesis testing. So so we are going to go through the steps of this hypothesis testing. So first we'll look at what hypothesis is and how to formulate hypothesis. When we do a research, we need to have a hypothesis. That's what we test for, right? So usually, a research question can be, converted to a hypothesis where we can test. So we use different kinds of tests to evaluate this hypothesis, like it's coming under this statistical analysis. So first thing we talk about is the t-test. Personally, I have not really used t-test from any of my publications or anything, but this is like the basic analysis work that we always do before we go into advanced analysis. But there are lots of people, they use t-test solely for their publications. It's a very versatile tool where a lot of people can make use of to understand if there is a significant difference between two quantities. So that's what we are going to do here. So the first one is one sample t-test, and the next one is two sample t-test, and then the next one is paired t-test. And then we also need to understand how to interpret p-values and confidence intervals. So again, I'm assuming you have the basic understanding of these concepts. So this is a method. Hypothesis testing is a method that we use to infer about a population using a sample data set. So now this is going to help us to decide if the observed data can be explained by chance. Chance is, we also call it random, or reflects a true effect. So if it is just random, so there is no use of it, right? But if there's a true effect, then we can determine that. So that's what we do through hypothesis testing. So we first formulate the null hypothesis, and then alternative hypothesis. We use these terms like H0 and H1 for these two types of hypothesis. And a null hypothesis represents no effect or difference between the two quantities that we measure. We evaluate. So that for example, there is no difference in average scores between group A and group B. For example, let's say we have a group from one company and a group from another company. So we measure the averages and we perform t-tests and see if there is a significant difference between two groups. So if there's a significant difference, that indicates some sort of different characteristics between two groups that could be evaluated further, using advanced methods. Or if we just compare, let's say, between two groups like male versus female, the substance use characteristics, substance use behavior is different. So that could, itself be your, hypothesis. So your research question, it could be this t-test could give you the final answer that you're looking for. So then you are done, and then you can write your conclusion. So if you get the results. The next one is the alternative hypothesis. So which represents a real effect or difference contradicting the null hypothesis. So there is a significant difference in average scores between group A and group B. So t-tests compare means of groups to determine significant differences using the t-distribution, which is useful for small samples or unknown populations of standard deviation. So this may not work when things get a little complicated. So especially if the sample sizes are larger, and also it's heterogeneous. So this may not really give you a lot of insight. So one sample t-test is actually to compare the mean of a single sample to known or hypothesized population mean. So we just compare a known or hypothesized population mean to a single sample that we have in hand. Its characteristics, mainly mean, right? So that's what we study. So we are going to assume that the data is, the variables are, observations are continuous, and they are normally distributed in the population, and then the independent data. So those are the assumptions that we make. And then we formulate the hypothesis. So the null hypothesis says, sample mean is equal to the population mean. An alternative hypothesis says sample mean differs from population mean. And then calculate the test statistics. And then determine the degrees of freedom and find critical t-values. And then compare t-statistic to critical t-value, and then interpret the results. So the next one is the two-sample t-test. The purpose is compare the mean of two independent groups to determine significant differences. So we have the same assumptions that we had for the one sample t-test. In addition, we have equal variances for these two samples, because when it comes to samples, variance also matters, because it's unlike populations. So I'm not going to again go deeper into all these things, because I'm assuming you know what I'm talking about. So I just remind you these things, and we'll go into the analysis. Okay. And then again, you follow the same steps that we did earlier to develop the two-sample t-test. And then the paired t-test is to compare the means from the same group at different times or under different conditions. For example, you say you have a group of people, you let them undergo some sort of a treatment, right? So you have the mean before the treatment, and then you have the mean after the treatment, right? So you see if there's effect of the treatment, you can determine using paired t-tests. So you have the mean before the intervention, whatever you did, let's say some sort of a treatment that you introduced, and then after that you determine the mean value before and after, and then you can determine if there is an effect of the treatment. So the assumptions are continuous. There are independent pairs of observations, and difference between pairs are normally distributed. Similar steps that you have to follow to do the paired t-test. And so p-value, we all know what p-value is. It measures the probability of observed data under the null hypothesis. When we say null hypothesis is true, what is the probability of having the observed data? So small p-value suggests that rejecting the null hypothesis. So that means we are refusing null hypothesis is true. CI, the confidence intervals, ranges within which the true parameter is likely to lie. So basically, you see what is the 95% confidence intervals. That means from the mean So what is the confidence that you can have regarding your results, right? So the outcome. And then conduct t-tests using the fabricated data set to understand the concepts better here. So we analyze the results and then interpret p-values and confidence intervals. In R, so we have the ability to create a data set, a fabricated data set, like however you want to do it. So here I defined all these variables, like 12 variables: ID, group, pre-treatment score, and post-treatment score. All are continuous. And then age, continuous, gender, binary, income, continuous. Likewise, I have 12 variables here. We won't use all these 12 variables, but I want to show you how to do this in R. So these things, I know you haven't done this, so we'll focus more into these things, okay? Not the statistical concepts much. Some of you probably know statistical concepts better than me. So, here how you, this is the approach of developing samples. So it could be any sample size. So set seeds, like, you just introduce some sort of a randomness into the program. So where we develop the data frame. So here we have the data frame. We have ID, so which is continuous going from 1 to n. So it's sequence. And then group, you have to say, either it's treatment or control. So it's randomly going to assign it. And then pre-treatment score, it's going to be normally distributed. Mean is going to be 50 and standard deviation is going to be 10. So you can see this is the pre-treatment score, and it's going to be 10,000 values, which has a mean of 50 and standard deviation of 10. So the R is going to use this program, this code, this function to generate random numbers with the mean of 50 and standard deviation of 10. So that's pre-treatment score. And then post-treatment score, purposely you say mean is like 55. So you can see we fabricated, right? So we added 5. So that means it's obviously we are assuming that post-treatment score is increased. So that's how you create a fabricated data set. So you can see age. So it's going from 18 to 65. So this is obviously going to be an integer. So going from 18 to 55. And gender, again, is a binary variable. So likewise, you can you can see everything else. It's pretty similarly I have defined, and then you can just run everything, and then you can see this data set. So just in case if you want to test something that you don't have a data set, this is a good way to fabricate a data set. Okay, so all right, let me clear this. And then show you. Here's the data set. Now you can see, the group, treatment groups, and the control group. And then we can see pre-treatment score, post-treatment score, age. So we have a data set here. All right. So again, it's not accurate, but it's good enough for us to do our testing. Okay. Okay. So let's go ahead and right. So one sample t-test. Okay, so we have t-dot test, like this is actually base R code. So this function is in base R code, and then you have to give the data. So pre-treatment score. Okay, so that's what we are going to test. One sample t-test. And then we are giving the mean value of the the population as 50, right? So if we do this, let's see what it's going to do. So this is the outcome. So compared to the population mean, which is 50, so it's giving a p-value of 0.849. So that means we are rejecting the null hypothesis, right? So that means, so we can say the true mean is not equal to 50. So, and the 95% confidence interval is given, so 49.82 and 50.21. And then the mean of x is 50.01. So this is the, the one sample t-test, which is so the population mean is given, and then from the data we estimate the sample mean. It is obviously around 50, but it's not exactly 50. So, but still you can see the p-value is 0.849. Okay. Okay. So then to sample. So we are going to compare between the groups, right? So the two samples this time. So we are comparing between the two groups, treatment versus control, right? So let's see, if there's a difference between treatment versus control. I mean, I don't know what we should expect, but obviously, we have a higher mean value there, right? So let's see what it's going to give us. So so you can see, if you get the mean value of the pre-treatment score, between the two groups, you can see there's no difference. So, but if you get the pre-treatment versus post-treatment, obviously there's going to be difference within the treatment group, right? That's what we assigned. So that's what we should expect. So, but ideally, so we don't get a significant p-value here. So that's what we see between the two groups before the treatment. If there's a difference between these two groups of the score difference. Okay. So now we are testing between the pre versus post, right? Before and after. So what would you get? Let's see what it's going to give us. So we are just doing the t-test. We just need to give us, we just need to give the program, what we are comparing. So this time we are comparing first argument, saying the pre-treatment score, and the second argument saying the post-treatment score. So it's paired, it's true. So when it's paired, so it's just going to compare before and after for each. So now you can see p-value is very significant, right? So that means obviously there's a difference. It makes sense because remember we assigned mean value purposely at 55, right? Post treatment and pre-treatment we assigned it at 50. So it makes sense to get a significant p-value here. So that means we can say we can reject the null hypothesis and say there's a significant difference between these two means. Okay, so I mean, in real world, you don't have this kind of fabricated data, so you never know what you're going to find, right? So maybe your treatment has no effect, right? So in that case, this could also be insignificant, right? So just be aware of that. So since my data is fabricated, so you can see you're getting that. Okay. Yeah, so in conclusion, t-tests are needed to compare group means and determine significance. So understanding the application and interpretation is critical for robust statistical analysis. So this could be, like I said earlier, this could be like the first step of your analysis or the final step. So some people would just use the results of t-test to write their discussions, right? So that's what t-test does, and then the chi-square test. So we also call this the goodness of fit and also independence test. Let's see what this test does. Now, chi-square tests are non-parametric tests used to determine if there is a significant association between categorical variables or if the observed distribution of categorical data differs from the expected distribution. So earlier, remember, we had mean values. They were continuous observations, right? So in order to compare categorical data, so we can use a chi-square test. So this test could be helpful in order to determine if there's a difference between two categorical groups, or if there's a distribution difference between the observed and then the expected. So again, so we have assumptions. Data is categorical, observations are independent, and the expected frequency in each category should be at least 5. If there is no frequency of at least 5, you cannot perform this test. So the null hypothesis for goodness of fit is the observed frequencies match the expected frequencies. So remember, in categorical data, we have frequencies, right? So for categories, for category 1, you have frequency of this much. This many people said, it's yes. And this many people said it's no. And this many people said it's inconclusive. Likewise, they're all frequencies, right? So that's why we talk about frequencies here. And then the observed frequencies do not match the expected frequency is the alternative hypothesis. So we compare the chi-squared statistics and then degrees of freedom, and then the critical chi-square value, and then compare the test statistics to critical values, and then you interpret the results with p-values. Okay. So this is one example. So a practical example. So testing if the distribution of substance use types, alcohol, tobacco, marijuana, among adolescents matches an expected distribution. So if we have an expected distribution or another distribution from another population matching the population of interest that we have or sample that we have collected, so we can test that also. So so that's goodness of it. And then independence says examine if gender is associated with substance use patterns among adolescents. So this could also be done because we are, it's goodness of fit test, but now this time we are testing for the independence. It says we are testing if they are dependent or independent. So that can also be achieved through this test. So interpreting the results involves comparing the calculated chi-squared statistics to the critical value or examining the p-value. So definitely we'll follow the same statistical assumptions that we made, significant level, null hypothesis and alternative hypothesis. So we have the confidence intervals that we usually assume that's significant. So we will again do a chi-square test using a fabricated data set. So I'm making 50,000 records, a sample. So that has 50,000 records with 12 variables. That includes categorical and binary variables related to substance use. So these are the variables. We don't have to go through them again because I explained how to do that. But let's try to run this. And for this one, I really would like you to try this. So in order to try this, you just have to copy and paste the code that I gave you. So you have it, in your slides, and then go to your R workspace, copy, paste, and then run. Okay. So this is where we do the chi-square goodness of fit test. Okay. So let's see. So this is where we create the data set. I'm going to clean this and clean this and then run. So you should have the data set. Okay. So as you can see, we have substance use type. So what kind of substance they use, right? So we said it's either going to be one of these three, right? And then gender, just binary, male versus female. That's how I assigned. You can have all like multiple gender types. So you just have to add them. Okay, you can add multiple substances here. You just need to add them here into this array. And then we have age group, right? So what age group that they belong to? Like, so you can see different age groups are given here. And then family income level, education, all these things are there. So you can at home, when you test this, so you can test for multiple variables. Let's say like you can use different sets of categorical data. I have included numerous categorical data here, as you can see here. So you can do the test for all of them. So observed and expected. So this is where the chi-square test is being performed. So what we do here is we actually have observed distribution here. We just need to get the, you have to use the table function. If you use the table function, it will show you, so the distribution of the substance use. So we had 50,000 records. Out of 50,000, 16,559 use alcohol, and then 16,746 use marijuana, and 16,695 use tobacco. So roughly it is like, equal, but it's not exactly equal, right? So it ideally should be like 33%, 333, likewise. That should be the percentage. And so these are the frequencies, right? So we just count number of occurrences. That's what's called frequency. And then the expected distribution is this. So we are expecting they are using all these substances equally. So that's what we expect. So let's say, so alcohol use, tobacco use, and marijuana use is prevalent equally. So that means, so you would see pretty much 33% of them are using alcohol, and then 33% using tobacco, and the rest is using pot. So you can see that's the expected distribution. And then, so you perform the chi-square test. You have to give the observed and then the expected, and then you find the chi-square test. So expected, if you run observed and then you print it, you would see the same table, and then expected, you run expected, and then you print, you're going to see these amounts, right? So it's because we multiply it by the total number of records. Sum observed means the sample size. Basically, so you can just multiply it by sample size. So you don't have to sum the observed. It's just like the total sample size. So n times 0.33 is 16,500. So you can see how it's being distributed. Okay. So the difference between this distribution and this distribution. So we are going to test if it is significant or not. So that's what you do here by computing the p-value here. Okay. So we can see chi-square test from the probabilities is given here. So chi-square value and then degrees of freedom, and then the p-value are given. So you can see p-value is 0.009. So we can see if we reject the null hypothesis or accept it, and based on that we can decide if these two tests frequencies are different. Okay. So pretty simple. So it's the same concept, again, like null hypothesis and alternative hypothesis p-value. They're just uniform. So it's universal. You don't have to change that. So any of those definitions. It's just we are comparing different things here. Just frequencies. Okay. And then we are doing the independence test. So here, let's see what we are doing. Sorry. So now you can see contingency table. Remember we talked about the contingency table last time. So we are just cross-tabulating gender and substance use. So for example, if you run this, you would see right here, this is cross-tab, right? So because we are cross-tabbing, you can see like female and male, they're coming in each row. Rows represent female versus male, and then the columns represent substance type, right? So you can actually, by looking at this, you can see if there are differences. But this chi-square test actually can tell you if there's significant difference. So yes, by looking at numbers, we can say if there's a difference or not. But in order to prove that using accepted or defined test methods or widely accepted approaches. So that's what these tests are needed. Okay, so we need some sort of a widely accepted method. We can just say, oh, you see, this value is higher than that value, but is it significant? So I have to also tell you that this significant, statistical significance is being challenged by numerous arguments. Some other statistical analysis methods, for example, like Bayesian inferences. So they have the alternative and null hypothesis defined differently, and they argue that this kind of significance is or falsifiable, or they even saying it's flawed. But still, this is widely accepted most of the time, which is most of the time, which is the case. Anybody can use. So we don't have any other option, and this could be the most predominant statistical method to test any hypothesis. So we should be in good shape. But eventually, when you learn some advanced methods like Bayesian inferences, so you will see how this is different from the this hypothesis testing. Okay. But for now, so this is a standard way to show people that these two things are different. These two quantities are different, not by just looking at the number, by using a standard procedure. Okay. So we have this table, and then when you do the chi-square test, it's actually going to tell us if there's a difference between these two groups, male versus female, of their substance use, right? Distribution. Sorry, I didn't find this. Yeah, so it looks like there's no significant difference. I mean, by looking at the numbers themselves, we can see there's no significant difference. Maybe in some cases, marijuana, and then maybe tobacco, but it doesn't seem significant. Okay, so that's why maybe the numbers could be misleading. So we need to perform acceptable testing. So people will, if you put these numbers in a publication and then write your conclusions, they will accept. So this is the standard practice. So if you had an argument saying that, okay, so between male and female, so these things differ, so you may have to drop your argument at this point, because this shows they are actually independent. So they're not dependent of each other. So if it differs, you can see if alcohol, this substance use, and female. So if there is if there's a significant p-value, we can say they are dependent on each other, right? So at this point, it's not. So let's move on. Yeah, so that's about the chi-square test. So we use that to analyze categorical data, and then they can show us give us insights into associations and distributions between those variables. Okay, so the next step is the ANOVA test. So ANOVA test, analysis of variance. So that's what it stands for. This is also widely used in many contexts. Like people use this in machine learning also, but we broadly use this to conduct one-way and two-way tests to compare groups. Okay. So we have one-way ANOVA test, and we also have two-way ANOVA test. So one-way ANOVA test is used to compare the means of 3 or more independent groups based on a single factor. For example, like age group. So it determines if there is a statistically significant difference between the groups. Again, keep in mind that statistically significant. So this is actually pretty controversial. Like, when I do my research, so, there are places where we don't really use some of these statistical um, um, concepts. So in especially in Bayesian inferences and also in machine learning. So you don't have this kind of hypothesis testing. So in that case, can you say it is significant? So that could be really tricky in terms of statistical perspective. So you need to really be able to show that statistically significant by performing a hypothesis testing. So p-value, it's like the only option that you have. But when you learn advanced things, you will realize that there are other avenues and there are other ways of proving this. So again, we don't need to get there. So this, in order to prove if it is statistically significant or not, we have to perform a test like this and see if there's a significant difference. So these are not just significant. When we say significant, it's always statistically significant. So it's preconceived. So in this case, you can test like 3 groups um, or more. So for example, when we compare mean substance use score across different age groups, so we know this is like just by doing an ANOVA test, you can determine if there is a difference between these age groups, their substance use. Obviously, there are advanced analysis methods. You can do like statistical modeling to see this. So that's one thing that we can do. But before we get there, this could, just this test itself can give you what you need. So pretty much the same, set of steps that we need to follow. So again, this is like hypothesis testing. So for ANOVA test, null hypothesis, all group means are equal, and alternative hypothesis, at least one group mean is different. Remember, it could be at least one group. So maybe it could be 1 or maybe 2 groups, but we can say at least one group mean is different. Okay. So here we compute F ratio, F statistics, and then degrees of freedom, and then critical F value, and then you compare statistics to critical value, and then you interpret the results. Always we use p-value to compare, right? So after finding a significant result in ANOVA test, so we can do a post hoc test to find which specific group means are significantly different. I mean, ANOVA test does not show what specifically, what groups differ, right? So it's just going to say it is different, but it's not going to specify what groups are different. But when you do your research, definitely you need to be more specific. Just by saying, oh, hey, with age, this substances changes, and some groups differ from the others. And then, the reviewers, whoever is going to reviewing your work will come back and ask you what exactly you're talking about, what groups are different. So that's where you need like post hoc analysis to fine tune your findings and tell people what exactly is happening, what groups differ. So this thing, this correction, this function, there's a couple of methods that they're showing here, and there's many other methods. These are some methods that I found that you can find out using these methods. After doing the ANOVA test, you can use these methods to find out, what groups really show significant difference. Okay, and then the two-way ANOVA test. So this test, you can consider 2 factors simultaneously. So, so in this case, so you can say, the substances differ, across the age groups as well as gender. So the mean, if you compare the means of different groups, I mean, so that's what we find through the two-way ANOVA test. It evaluates the main effect of each factor, but also the interaction effect between factors. So interaction effect is not something that we discussed before. So, but when we possibly when we get to the statistical modeling, so especially when it comes to linear regression or multi-level regression, if time permits, we'll talk about that. So basically, interaction is like interaction between two and how it impacts the outcome. So age and gender together influences the difference, the main effect. So that's what we investigate through the interaction effect. So, for example, if you have an outcome variable, so here we are testing the means, right? So we select substance use mean value, right? And then we see with age group how it changes, with gender how it changes, and then we also see the interplay between gender, age, and how it impacts the outcome. So that's the interaction effect. Okay. So which is significant in many cases. You may have an interaction effect in multiple cases. Okay, so again we have a hypothesis, the testing for two-way ANOVA. So for that we have null hypothesis. There is no main effect of factor one. That's age group, and then also we say there is no main effect of factor two, gender. And then also we say there is no interaction effect between factor one and factor two. So all these things are included in null hypothesis. And then similarly, we can define alternative hypothesis also. Okay, it's just the opposite of null hypothesis. And then calculate the ANOVA statistics, S ratio for each effect. And then the degrees of freedom, critical F value, and then test statistics, compare them, and then you interpret the results. Okay, at the same process. And then we have an activity. So I don't know if I gave you enough time last time, so but this time I'm going to give you enough time to like at least a few minutes to go over this. Okay. So let's take a little time. So because I want to make sure you can do this. Okay. So I can explain what these things are, but I'm pretty sure it's self-explanatory. Okay, so yeah, so ID, age group, yes, we have different age groups here, gender, male, female. So these are the things that we are going to compare, and then we have substance use score. So you can see we have 5 groups here. So each group has different mean values. So the first group has mean value of 60, and the second group 55, 50, 45. So you can see that's how I created it, right? So so that's actually being considered as this 5 age groups. Okay. So and then so you can see when we run this. Sorry, I have to define n. So you have data set that I have expanded to include the group these group differences. Okay, so you can see exactly 1/5 of the population is going to have this mean value. The random numbers coming with this mean value, and then the standard deviation of 10. So you can play with these numbers and see how it's going to interact and impact your outcome. Okay. So this is how it's going to be like, the data. So I have all these variables just for you to play with, and then kind of perform your own tests and see, develop your own hypothesis, look at the data and come up with some possible hypothesis and test at leisure and practice them. Okay. So I'm pretty sure you will also get a real world data set from the from the organizing team, and you might be able to use that. And then let me. So now that's the data set. So let's also do the test, and then this time again I'm gonna give you some time. Okay, so because I want to make sure you can do this. So you can see this is one way ANOVA test, right? So because we are comparing substance use score and age group, right? So this is definitely one-way test. So let's run this and see what it's going to give us. So there's a p-value of 0.318. So that means the relationship this between the age and this substance use group is being reflected by this p-value. So you should be able to interpret. So whenever you see the results, mainly p-value, and you should also understand what these residuals and degrees of freedom, the sum of squares and mean squares and f-value, these things you should clearly understand. You have learned this in statistics class. Okay. And I really want you to now run and see if this is working. Okay, so please take a moment to do this. Okay. So I can see some. I don't know. I cannot hear anything.
Yes.
Hello.
Yeah.
Oh, Verna. Okay. I thought there's a problem with the technology or something. I thought
No, you're doing good.
So
Thank you.
okay. No, yes, I went a little fast because in the beginning, it was just like statistics, so I didn't spend a lot of time because I wanted to spend a longer time, with R. And, I see in the message, I checked some messages here, so you want me to explain the code. So I don't know if you were here last week. So I explained, what these things I know function, the arguments. So I'm not going to go through all that. And also, I think I explained enough about, the data frame and how it is being created. So, but all these things, we always use these functions, and then we have all these arguments that we execute, use through the functions. So these are nothing but functions, function within a function, and then we use all our logics within that. Okay, so again, like these things we talked last week, so I really want you to go back and revise them. That's why we learn all the basics, and then we go into the analysis using the functions that it's already like, inbuilt. But feel free to like let me know if you still need like further clarification. Okay. So previous session materials are being already shared, right? I think we have shared the previous materials, right? Have we?
Yes, that's correct, as well as the recordings, but not unless they only registered this week. But no worries, we can send it to them again. Thank you. Dr. Kasgola, sorry, like to interrupt since you are listening to me. There's a question though. Do you have any specific statistic book that you need that you use as reference for this presentation? They were asking if you can
Uh,
share the author and the title, please. Thank you.
Sure, yeah. So I am actually using some of the courses that I've taken during my undergrad a long time ago, and also during my PhD. So basically, like, I'm not following a specific textbook, but I can definitely, by the end of the course, I can give you a couple of good textbooks, because some of these textbooks that we use are maybe not really like up to date. So I'll find a couple of good textbooks and give them to you. But these are actually through my undergraduate and then PhD courses. That's where I learned most of these things are from. And also, there's a lot of content that I learned through the R manuals. All these. Like I said, like last week, so you can learn a lot through these user manuals for each package that we import here. So last week we imported so many packages. So there's a user manual. So it explains how to use these functions and what it can do. But the basics definitely, so programming basics that I learned through my bachelor's and PhD programs. So several courses. Definitely, I'll give you a couple of good statistics books for you to review.
Thank you, sir.
Welcome. Okay, so I hope we had enough time. Let's proceed. And so this is where, so now we test if this test, we tested for like, we did the one-way ANOVA test and see, check if the results are significant. And then we can also run this post hoc analysis and see if there's any groups that we can find out any significant results. So you can see there's no any p-value that is significant, right? So so we can see the notice. It's comparing two groups, and it's also giving the difference between the means, and then in the end, it's giving us if it is significant or not. So that's none. So I mean, we also got like this p-value is not significant, right? So no wonder we don't have it. So, but if you play with the data set, so you might be able to find good values, or you have to use a real world data set. And if you really know, there's a difference between two groups, and then you can compare them with the substance use, right? So there will be relationship between, that means there's a different dependence between substance use and age group. Okay. Since this data is fabricated, I'm not getting that. And then this is the two-way test. Let's do that also. See, the two-way test, we have an interaction, right? So AOV, is the function, that's analysis of variance, and then we have the first um, argument where we define the function, and we have gender interacting with age, right? So we use this. So this is the multiplication sign, right? In the computer, so we use this as a multiplication sign, right? So age multiplied by gender is actually the interaction. So we are including interaction between age and gender to find the effect, the relationship with the substance use score. Okay? So that's what we do here. And if we run this, we should be able to get the results. So we can see that none of the p-values are significant. Age and the substance use score, p-value is not significant. Gender and the substance use score, p-value is not significant. And so we can also see the age group is not significant. So age group is not significant. Gender is not significant. So there's age group and gender interaction. Okay. Yeah. So try this and then make sure it's working in your environment. Okay. So in summary, one-way and two-way ANOVA tests are important for comparing mean across multiple groups and examining the interaction between factors. So when we have significant results, we can perform post hoc analysis to identify specific groups that are different. Okay, all right. So that concludes this first part of the statistical analysis, where we performed the t-test and ANOVA tests. So those concepts, again, so you start from the simplicity and go to the complexity. Okay, so you don't start your model with a complex multilinear regression analysis. So you start with descriptive, and you go to do a t-test, perform a t-test, and see how things differ between the groups that you are interested in, and then you go into further analysis as needed. Okay. So if you need to support your argument, your research questions better, so you may need to dig deeper and perform further analysis. So that's all about the next section, regression analysis. Okay, again here, I'm not going into the fundamentals, but I'm just going to. I have some notes written here. I'll just read them through and then explain a little bit. Okay. So it's really simple. Linear regression. We assume linearity. So linear relationships are actually, I think you know what I'm talking about. Linear means it's making a line relationship between x and y, right? X is the independent variable, y is the dependent variable. So simple linear regression, we assume they linearly vary, right? So when x changes, y also changes, but in a linear manner. So it makes a line. If you draw lines, if you identify those those points that we observed, in an XY coordinate system, it will make a line. So simple linear regression, it assumes it's the word itself says that simple, right? So it is simple and it's linear, and we are going to assume it is correct for our data set. So fitting a linear model, it is actually involves fitting your data into this simple linear regression model, and then see how your data and then the model differ, right? So you have the model, and then you have the data, right? And then you also see the difference between your observations and then your model parameters that you found, right? So observed values that you have, and then those are the actual values, and then the values that you find through a model, then you see if there's a difference. That's where you also determine your fit, if the model really fits well. So that comes under fit indices. So basically, like if I draw this, let me explain this a little. Because this is I'm trying to get my I'm just gonna draw it here. Okay. So these are the axes, okay? So you can see, so we have x-axis and y-axis. So this is x, and this is y. So now we got observations, right? So let's say we have observations here. This is what our observations are, okay? I hope you can see my, dots, right? So these are the observations. So basically, by looking at this, we can see when x increases, y also increases, right? By looking at the points. Can we say that? Yes. So with that assumption, we are going to define a model which is actually going to be, y equals mx, so which is actually a linear model. So it's represented by a line. So it's going to be something like this. Okay. So this is going to be your regression line. So let me use a different color, like this. So the difference between the predicted, whatever that you have estimated using the model, the values and the points, the model says all the points are going to be on this line, right? So that's what it says. But actually, you can see it's the actual observations are not actually coinciding here, right? So it's different. So that difference we evaluate, as some sort of a fit, how well the model fits with the data. So if this difference between the actual and then the model computed values is really high, we are going to say that our model does not fit well with the data. So that's where we talk about the fit, right? I mean, for example, let's say, so you cannot say, let me say, if we have our data going like this, right? Hold on. Why it's not working? So definitely we have a problem, right? We cannot say that, right? So we cannot draw a line like this, and we cannot say they fit well. So you can see if you compute the distance between these points, points that we draw on the line, and then the points that we actually have observed. And if they're too far from each other, we can say they don't fit well, right? So this is like the basic concept of determining fit. So, but when it comes to like advanced modeling, it gets more complicated because we have 2, 3, 4, 5 dimensional spaces that we cannot really comprehend, in our brain. So, but just to just to make it like more simple, this is the simplest way of determining fit. So, does it fit well? It's like your suit. If it fits well, then that's good. If it doesn't fit well, that's loose. It's not good for you, right? So same thing. It doesn't represent the model. Okay, so the data does not represent the model and vice versa. So that means we have to come up with another solution. That's why it's really important to determine what the fit is going to be. There are lots of simple and advanced methods to determine the fit of your model. Okay, so we'll try to understand some of them. Okay. See, so that's why we try to estimate. One of the most fundamental ways of evaluating fit is, fit is using the R squared value. Okay, so again it's basically computing the distance between those observed points and then the determined points, okay, from your model. So that's what we are going to do here. So again, simple linear regression is a statistical method that models the relationship between dependent variable and independent variable. So there's only one dependent variable, but you may have multiple independent variables. Then it does not become simple linear regression. That becomes multiple linear regression. So we are going to get to that. But in this case, in simple linear regression, you only have one dependent variable and one independent variable. Okay, and the relationship is always assumed to be linear. Okay, so in that case, so we have this equation. To determine the linearity. So where in this equation says y equals beta naught plus beta 1 times x plus epsilon. So where y is the dependent variable, x is the independent variable, and then beta naught is the intercept. Okay, so intercept is actually where the line cuts the y-axis. Okay, and then beta 1 is the slope, what the slope is, that makes that line makes, and then epsilon is the error term. So there's always going to be an error, right? So that error is actually going to be the residual. So whatever is not being predicted or modeled by this equation is just going to be a residual. So that's being considered as an error. So if the error is high, so we may have a really poor fit, right? So that's what we are going to get. So when we fit a linear regression model, we just need to determine these coefficients, beta 1, beta 0, and beta 1, okay? Which minimizes the sum of the square difference between the observed values and the values predicted by the model. So that's what I explained. So those points that I explained, so we need to find the line that makes the shortest sum of these distances. Okay, so we square them because we don't need to have any negative numbers, right? So if we have negative values, that would be a problem, right? They will cancel out and they will give us misleading results. That's why we find the differences between the actual observations and the predicted or determined values by the model, right? Which are the points on the line, right? That red line. So we basically try to minimize the residual sum of squares. So then we can bring our line as close as possible to our observed values from the data set, right? So then we can say our line represents, the observed data, right? So this process is typically done using methods of least squares. So we use like simple algorithms to iteratively do that and determine the best fitting model. Okay. So there's some mathematics, some advanced mathematics behind this. You don't have to know all that. All you have to know is that there's like minimization algorithm that actually minimizes this error. So yeah, so this explains what intercept and slope is. I already explained that, and then this explains what R squared value is. So let me just tell you. I know all of you know what this is, but just for the reference, the R squared value represents the proportion of the variance in the dependent variable that is predictable from the independent variable. So it ranges from 0 to 1, where 0 indicates no predictive power and 1 indicates perfect predictions, right? So if R squared value is really close to 1, we can say, the dependent variable and independent variable are really related with each other. So that has a high predictive power. So the dependent variable has really high predictive power to predict the values of the independent variable. So now I think I have a small activity for us to do a simple linear regression model. So I think before we get to this, we can take a break. Am I correct?
Yes, please, sir. So let's have a 15-minute break.
Okay. Okay. All right. So I'm gonna end the call and I'll join again, and then in 15 minutes I'll be back.
Thank you, sir.
Okay. Thank you. Another one. Okay. So then we add another predictor. So likewise, one by one add predictors. If and only if it improves the statistical significance or model fit. Okay, so that's what's called forward selection, and backward elimination is like have all the variables added as predictors or independent variables, and then one by one you take them off and then make sure if model improves. And stepwise selection is a combination of forward and backward selection. So for example, if you go back to our data set, so it's where is it? It's here, right? So this was our, remember, this was our, dependent variable, right? Dependent variable. So we considered age as one predictor and independent variable. So let's say we got an R squared of point 0.5. And then we try to add like education level or maybe like income level, right? So then when we add both of them, it becomes a multiple linear regression. So it's not just linear regression because we have two predictors, two dependent variables, right? And then we run it and see if it improves, right? If it's not going to improve, we remove income level, then maybe try to add something else, right? So like health score, maybe sleep hours or something like that. So you keep on adding things until it gets improved, but you delete, remove it if it's not improving the model, right? So that's what we should be doing. So while doing this multiple linear regression, it's not like we are using all the variables that we have in our data. Okay, and it's also important to check these assumptions if they satisfy. So the biggest drawback in this kind of statistical testing is actually these assumptions. So we assume these things, but they could not be reasonable to assume, depending on the complexity of the data. But unfortunately, at this level, there is nothing that we can do, because they are unavoidable. So you cannot do anything without assuming these things. Number one is the linearity. So we always assume the relationship between the predictors and the dependent variables is linear. Okay. So we have that assumption, like we said before, it can be represented, with one single line, right? And then the second one is the independence. So the residuals are independent. So I'll explain this a little bit when we get to the next steps. So what this independence means, like residuals of each and every predictor or the dependent variable should be independent from each other. And then homoscedasticity. So this is the variance of the residuals. It's constant across all levels of the independent variable. So that is also important, homoscedasticity. I'll explain these things. I think I have some more slides where I explain all this. And then normality. So we also say the residuals are normally distributed. So again, I'll explain that also. And the fifth one is multi-collinearity. So multi-collinearity is actually make sure we don't have predictors that are highly correlated between each other. So these are the things that we need to test before we do any of these things. So most of the research, I have seen a lot of people do this, but there's also some research people do without performing these tests. So because simply they don't know these things exist and they have to do these things, or simply they haven't really get into the depth and breadth of the statistics and what they're doing. So yeah. So in order to ensure the validity of the multiple linear regression model, it is extremely important to check these things. So let's start with linearity. So how do we check that? So linearity is the assumption that we make to tell that there's a relationship between each predictor variable. Again, predictor is another name that we use for the independent variables. Predictor variable and the dependent variable. So So the relationship between each independent variable and the dependent variable should be linear, each relationship. So if we have two predictors, so the first predictor and the dependent variable should be linearly related, and then the second one also should be the same. This can be checked using residual plots, where the residuals should scatter randomly around zero without any clear pattern. Okay, so I can show you what those residual plots are, and because we are going to plot them, I think I have some R codes, but we need to understand what these things measure. Okay, so we'll explain, we'll get to that, and then I can show you what it is. So that's how we check. So we create scatter plots for residuals versus predicted values. So we need to look for a random distribution of residuals without a discernible pattern. So then we are good to go. So that means we can say it's linear. Otherwise, we have an issue and we cannot proceed with the multilinear regression or any linear. So we cannot assume that relationship is linear. So there are conditions where actually the relationships can be nonlinear, right? For example, with age, like health condition, and it could not be it could not be linear, right? For some people, it could be like, exponential. For some people, it could be like, logarithmic. You never know, right? So, but obviously, it deteriorates, the health condition with time, but we may not be able to assume the linearity. But you can definitely check that using this linearity assumption. So you should justify your linearity assumption. So you cannot simply write in your article saying that, oh, we just assume it's linear. But how do you prove that? So well, this is the way to prove that. Okay. So when you have this, you have a solid argument. See. So I have all reasons in this world to assume this relationship is linear because that this plot does not have a discernible pattern. Okay. And then the independence assumption. So the independence assumption requires that the residuals, again, these are the errors, are independent of each other. So this means that there should be no autocorrelation among the residuals. So this is also really important. So so we have to make sure that the residuals, like let's say for predictor 1 or the dependent variable 1, we have residuals, and dependent variable 2, we have residuals. If they are related to each other, so we have a problem. So we have issues. So we call that autocorrelation. Especially this is very critical when it comes to time series data or when it comes to longitudinal data analysis. If there is autocorrelation, we have issues. We cannot really predict or determine what the trend is with time. It's because it's autocorrelated. So that means they are related. So the plot or the residuals at this time are dependent with the residuals of the other time. That means there is something happening in between these times that we have not observed, right? So and also the same way, we say independent variables, two independent variables are independent, but we can see if something is happening between those independent variables. So definitely they're not independent. They are dependent on each other. So our independent assumption is violated. You see that? So this is also very important to prove that, okay, these two variables are truly independent. That is why we can assume they are independent of each other, and we can consider them as independent variables in our model. So we can use this Durbin-Watson test to detect autocorrelation in the residuals. So a value close to 2 indicates the residuals are independent. Okay, so that's one way to do that. And again, there's lots of other ways to do this. So test for independent assumption, if you Google, you will find 100 different methods of doing this. And then the next one is homozygosity, which refers to the condition where the variance of the residual is constant across all levels of independent variables. If this assumption is violated, it can lead to inefficient estimates and affect the hypothesis testing. So, this says, the variance of the residuals is constant across all levels of the independent variables. So it should be constant when, when it changes, like when the variable, value increases, the variance should not change, it should not fluctuate, right? So that's what's called homozygosity. So we have to plot the residuals against the predicted values, and then we have to look for a constant spread of residuals across all levels of the predicted values. Then only we can say, it can be reasonably assumed that, there's homozygosity exists. Otherwise, it could be heterozygosity. So then that could be a problem. We cannot rely on our findings in that case. And then the normality. So the normality assumption means that the residuals of the model should be normally distributed. So this assumption is also really crucial because, when it comes to hypothesis testing, we have multiple residuals for multiple predictors, especially when it comes to multiple linear regression. So we need to make sure that this normality assumption is satisfied. So we create a QQ plot of the residuals and look for the residuals to follow the diagonal line, which indicates a normal distribution. That's how we should determine normality. And the next one is multi-collinearity. So this occurs when two or more variables or predictor variables in the model are highly correlated with each other. So if they're highly correlated with each other, then we have a problem. So multi-collinearity can cause lots of problems in different prediction models. We may not be able to see those problems until we evaluate them like this. That's why before we get into the model and get the results, these tests are really important. So if not, you're going to get into a really inconclusive or maybe even conclusive results, but which are really incorrect. So just because you have good model with good p-values, does not mean that the results are accurate unless you test for all these assumptions. So all the assumptions that you made should be justifiable and reasonable and testable like this, and then provable. So so we check multi-collinearity using the variance inflation factor for each predictor. So you don't need to know what it is and how it's being computed. You just have to check, if VIF value is greater than 10, because you need to first understand the concept, in multi-collinearity to understand what collinearity to understand what VIF is, and that's not necessary at this level. You don't need to understand all that, but at least you need to know how to estimate this and show that this is not violating this assumption. Okay. Again, this could be a huge problem in your model if you don't test that. Okay, so so yes, so this is explaining how to test these things, and I also have put why it matters and how to test again, in a more elaborative way, so you can go through that and try to understand all that. And I explain all that. Independent test, homozygosity, normality, and then multi-collinearity. Okay. Yeah. So I have an example that I'll explain that to you later. But first, let's try to create a data set, and then we should be able to use that data set to do this testing. Okay. Um, Wait, okay, I'm trying to find where it is. So I haven't, yeah, I think this is the data set. Okay, so um, unfortunately, I have not created data set for um, this test. So why don't we stop here for today because we covered big content today. So I really want you to understand what these concepts are, and then tomorrow, I spend like an hour or so to finish the rest, with this, and then we'll do a complete example. Okay, so I'll have a data set for you, and then we can get some hands-on experience. So I will also show you how to download a data set, and then we do some imputation, and we do all those things that we did so far, and then we'll get some hands-on experience. Okay, it's not going to be the best data set, so feel free if Verna, if you have a good data set that we can use tomorrow, that's fine. Otherwise, we can use what I have. So I feel like we covered a lot of topics today. So and then it's better for you to just try to understand what these things are.
You are right, sir. So thank you, Dr. Kosgola, for a wonderful session. Guys, as a reminder, recordings and PowerPoint presentation, as well as some screenshot of the images that I have taken, will be sent to you tomorrow morning. So wait for about 8 to 12 hours before you will receive a copy. There were also questions with regards to the certificate, and we would like to tell you that we will provide you with certificate. Just send us an email if you need one, but it might take us some time just to make sure that we are able to capture your hours correctly. So if there are no more questions, and again, we would like to thank Dr. Kosgola for taking his time to share his knowledge with us. And that's it for today. So we'll see you again tomorrow. Have a great rest of your day. So goodbye, everyone.
Thank you.
Thank you, Dr. Kosgola. Thank you. We hope to see you again tomorrow.
Thank you.